Okay, hello everyone. We'll get started. I'm Tony Roskilly. I'm Professor of Energy Systems here at Durham University, and I lead the EPSRC Network Plus on hydrogen fuel transportation. This webinar is part of a series looking at different aspects of hydrogen research applied to the transport sector. This month, we're delighted to welcome two speakers. One from giving an industrial perspective and one from academia. Let's move on to our first speaker, which is Eric Schuenemann. He's a systems engineer, manager of the systems engineering power subsystem subdivision of Robert Bosch. He's published many papers on the development in combustion engines and powertrains, and he will present on the activities of Bosch and what they've done so far in terms of addressing the challenges of hydrogen combustion. So Eric, please share your screen and give your presentation.
Thanks, Professor Roskilly. Thanks a lot for the introduction and for the opportunity to have this talk. We are a technology company. Our roots are mainly in automotive, and we are worldwide. We are still an automotive supplier for worldwide mobility solutions. And my focus of my work, of the group, of my department is combustion systems and emission concepts for light-duty vehicles with spark ignition engines. When we talk about the pathways towards CO2 neutrality or CO2 neutral mobility, we as company are working on all pathways. We think it has a lot of shortcomings to focus only on one technical solution, be it battery, for instance, be it battery electric. That sounds simple from first look, but it's important that, of course, the CO2 is not a tank-to-wheel discussion. CO2 emission, it's of course a well-to-wheel and a life cycle approach that we need to follow. And we think that, of course, battery electric vehicles are part of the solution, but they are not 100% of the solution. We need to consider all pathways because the customers, the use cases and the different regions will have different pathways towards CO2 neutral mobility. And that means in addition to electrification, we also are continuing our work to improve combustion engines, which can, together with drop-in renewable fuels like e-fuels or biofuels, second generation, can become carbon neutral too. That has been recognized recently by the EU Commission. And the EU Commission is opening up the legislation towards acceptance of e-fuels only driven vehicles beyond 2035. And that secures the long-time future of internal combustion engines. When it comes to hydrogen engines or hydrogen as a fuel, as a transportation fuel, we noticed that there is a lot of activity recently. Of course, in the field of fuel cell electric vehicles. However, we think that complementary to the fuel cell, the hydrogen engine is a very interesting and attractive solution. And that's why we are working on the topic. I would say again, the hydrogen engine is not so new actually, but there are a lot of, let's say, technology bricks that are in development or are available right now that have not been available maybe 10 or 15 years ago. So the hydrogen engine gets a lot of momentum at the moment and is a very important part of our work. Looking at the criteria pollutant situation, I would like to mention that this question from our point of view is solved even for gasoline and diesel powertrains that include latest technology that can be seen when we look at air quality monitoring stations. For instance, here close to my location in Stuttgart, we have, let's say, an inner city traffic hotspot. And here, in the past, we had severe or relatively high, I would say, concentrations of NO2 in the ambient air, which is specifically also due to the measurement location, which is 1 meter distance to a 6-lane road, and where we have no setup, where we have no air exchange basically, and that leads to a relatively, let's say, high emission or air quality situation. But we can see in the last around 7 years, this NO2 level has been massively reduced, and the main driver for this was the introduction of the new technology, which was or is rolled out in the new vehicle fleet according to Euro 6 RDE legislation. So very important legislative step that has pushed significant improvements regarding emission technology. And our estimation here is that when we have rolled out these vehicles into the existing fleet, the contribution to NO2 air quality is negligible. Same situation for particulates. So here we can take a look into the UK situation. So PM2.5 contribution or share from road transport in the UK, that has also massively reduced when we talk about exhaust emission related PM2.5. Of course, that is the introduction of the particulate filter, first for the diesel powertrains, but since Euro 6 RDE legislation, so since around 2017, this technology is also introduced for gasoline engines, and already now the exhaust emission share for PM2.5 is the smallest contributor when we talk about road transport origins. We have abrasion, so the road abrasion of particles. We have tire wear, so the tire abrasion and brake wear, and these contributions already now are bigger than the contribution from the exhaust. So we think that the air quality has massively improved with the introduction of the new technology, and even gasoline and diesel vehicles do not contribute significantly anymore. Actually, this will get better with hydrogen engines because in hydrogen we have no carbon. That's why also particulate emissions, and I would show later also that NOx emissions from hydrogen engine vehicles are significantly lower than I showed you for the latest diesel and gasoline technology. I mentioned that the interest is pretty high at our customers at the moment. More than 130 worldwide OEMs or manufacturers are interested in planning or already running hydrogen engine R&D projects together with Bosch. And you see that's a pretty, let's say, widely distributed situation. Of course, there's activity in the EU, but I would also like to point to Asia. China, for China, hydrogen is a strategic energy carrier. Same situation, of course, for Japan. They have for a long time committed that they will become a hydrogen society, so to say. Of course, they need to import a lot of their energy or most of their energy. The situation is, let's say, alike for Korea, China, I mentioned, and very interesting, India. In India, we see massive investments in green hydrogen production. It is supported by Prime Minister Modi because India would like to participate in the hydrogen value chain. I think that's very important because they import a lot of their oil at the moment, and they see hydrogen as a strategic energy carrier in order to reduce the dependence from oil imports. Same situation for China, and in order to basically participate in the green hydrogen value stream. The same is actually true for a region or for a continent that is mostly marked in gray, which is Africa. We are very surprised how quick certain countries in Africa have entered the topic of green hydrogen production and of setting up hydrogen value streams. And in this case, it also includes the transport sector. Because if the green hydrogen can be produced cheap and can be transported in a low cost situation, that means locally, for instance, with pipelines, then the price at the pump is very attractive and could be even more attractive than for drop-in gasoline or drop-in diesel e-fuel, and also could be more attractive than electricity. So that's why a lot of countries in Africa are jumping on the hydrogen value chain at the moment. When you look at hydrogen as a fuel, there are some, from our point of view, very favorable properties. We need to make sure, however, because hydrogen it takes in a lot of space because it's a gas, we need to make sure that we get the hydrogen into the combustion chamber, preferably with direct injection. So we are focusing our work on hydrogen direct injection. There are some challenges, but this is from our point of view most attractive situation. The hydrogen engine will be a lean burn engine because the ignition limits are very wide. It is no problem to operate a hydrogen engine with a homogeneous lean mixture that has a lambda 3 or 4. So no issue with this. And that's, of course, very helpful because it reduces the peak combustion temperatures, and that means thermal NOx formation is actually frozen. So no or almost no thermal NOx if you run the hydrogen engine at a lambda 2.5 or even more lean. On the other hand, auto ignition temperature is pretty high. So using hydrogen in a diesel combustion process is probably almost impossible. You always need, if you would like to run hydrogen in a combustion process, if it's a diesel process, you need a pilot fuel. That means a second fuel, for instance, diesel, that can have a compression ignition like a diesel process, and then can ignite the remainder of the fuel, which is then hydrogen. We focus, however, on spark ignition hydrogen engines. That means we use a spark plug in order to ignite the mixture. Interestingly, the ignition energy that we need is around 1 order of magnitude lower than for gasoline, so very low ignition energy. So there are very interesting properties. The combustion speed, as you see, laminar flame speed is also significantly higher. But that is helpful actually because in a lean burn concept or lean burn combustion, we have then again a reduction of the flame speed again. So that is a very nice fit from our point of view. That's why we're focusing on lean burn H2 engines with spark ignition. That's a system, as an exemplary system for a hydrogen engine. We have the intake air that is provided by a compressor of the turbocharger. We have then we have a charge air cooler here, and then the fresh air goes through a throttle flap into the engine. Cooled EGR is an optional, let's say, feature that we could have for some use cases. The hydrogen itself is then either provided by a port fuel H2 injector or by an H2 direct injector. For light duty vehicles, it is mostly H2DI. For the heavy duty vehicles, we have also due to shorter time to market and less changes on the engine, we also see port fuel injection system or variants. But H2DI is very attractive solution. The challenge is the actual injector, which we are working on. Ignition, let's say some changes on the ignition system, but I would say no rocket science here. We need to modify the spark plug a little bit, but otherwise, I would say no rocket science, no big challenges. The combustion product, which is of course N2, yeah, which is in an inert gas, so not a product of the combustion, and mostly H2O, so water vapor is the combustion product. These are then routed to the turbine of the turbocharger, provide energy for boosting the system. And after the turbocharger, we have the exhaust after treatment system. We still think we need elements of the after treatment system. Number one, an oxidation catalyst that takes care of remaining hydrocarbons and CO. Where do they come from? They come from the engine oil. So the source of these pollutants is only engine oil. I will show you in some later slides. The quantities are very, very low, so almost negligible. Oxidation catalyst is also important for another component that we have in the exhaust gas that is unburned hydrogen. So we have some unburned hydrogen. It's not a pollutant. However, we need to make sure that we get this converted, which is not a problem with an oxidation catalyst because we run the engine lean. That means we have some oxygen in the exhaust, and that oxygen reacts with the H2 to H2O in the oxidation catalyst. Then we use a particulate filter. We always recommend to use this. What kind of particles do we have? Also, the particles can only come from the engine oil, so from the combustion of engine oil that we have in very minor quantities. And then for the main pollutant that we have is still an NOx. Yeah, even though we run lean burn engines, we can reduce engine out NOx via relatively cool combustion. But it's not zero, so we need an after treatment, and that after treatment system is basically carry over from the diesel. AdBlue is injected, and the NH3 then reacts with the NOx inside the SCR catalyst. So also no rocket science. Basically, that is a solution that is available from diesel technology. We are positioning ourselves, we as Bosch, as a system supplier. So we are targeting and we are already working on the development of components that are required for the engine. We also develop a software platform for the engine control unit of hydrogen engines, and we also have engaged in hydrogen tank system solutions. We see currently as a mainstream a 700 bar gaseous H2 tank system in let's say some less costly, I would say, applications. We might also have 350 bar, mainly in developing countries. They will probably start with 350 bar. In the EU, also in Asia, the situation is that we have 700 bar gaseous H2 tank systems. Quickly on the injection system, I already mentioned that we are focusing on the direct injection. In this case, it is low pressure direct injection. There are also some activities in the market where market participants are using high pressure direct injection, which might give some, let's say, benefits regarding combustion control. On the other hand, it either reduces the driving range because you cannot run your 700 bar tank empty, or you need an additional compressor to bring up to increase the injection pressure or the hydrogen pressure for the injection again. And let's say on the right hand side we have this kind of diesel-like combustion system, but this needs a diesel pilot injection. So basically we have two fuels then. So we are also not focusing on this right now. Our focus is low pressure DI, and low pressure means a range of 40 bar injection pressure. When we look at the hydrogen gas jet of the injector, we see that the gas jet development is very sensitive to a potential guiding of the jet. Normally, the injectors that we are using for hydrogen injection are hollow cone injectors. So they produce basically a hollow gas jet with a cone angle of around 90 degrees. And this configuration might not be optimum for achieving optimal mixture formation. So we need some, I would say, devices or some measures in order to guide the gas jet. And one very simple measure is simply to reduce the injector tip protrusion in a way that basically the bore of for the injector inside the cylinder head is guiding the jet downwards. So I hope the movies are running. I just let it run. That is high-speed Schlieren technology that we have used here in order to visualize the gas jet. You see the time running here. And what also is very nice at the start, you see shock waves. So for the people in the call that are keen for gas dynamics, that's a nice feature that you can make visible. So that these waves are traveling with speed of sound, so Mach 1 basically. And you can very nicely guide the jet with these kind of jet guiding caps. So if you need to bend it, or if you need to have kind of a multi-hole or multi-spray setup for some applications, that is helpful. And in this case, you can do this via applying these kind of jet guiding caps. Quickly some engine measurement results. This is a heavy-duty engine here. On the upper line, we see upper part of the picture. We see the diesel engine, and on the lower part, we have modified the engine towards hydrogen engine. And what we can see regarding NOx formation, that is engine out NOx, so NOx that is produced by the combustion basically. We see that the engine out NOx emissions for hydrogen as compared to diesel are massively lower, so factor of 6 or more lower. We still have favorably high temperatures, which are important for for promoting the AdBlue SCR reaction in the aftertreatment system. So also here, the hydrogen engine makes it a lot easier to achieve ultra low tailpipe emissions. So we are convinced that the hydrogen engine has even lower impact on air quality than modern gasoline and diesel solutions. Then the question of efficiency, that's also very important to touch, because if we compare the hydrogen engine powertrain with the fuel cell electric powertrain, the fuel cell has much better efficiency, but this is only true for relatively low to medium power. So if you drive your powertrain with high, let's say, power requirements, then the fuel cell power is reduced, and the hydrogen engine powertrain, so the power of the hydrogen engine powertrain might even be, or the efficiency of this might even be higher. How can we achieve this for a light duty, so for a passenger car application? That is hybridization, because the hybridization, so electrification of the powertrain in a hybrid situation, increases the power where the hydrogen engine is driven. And that is actually done here in this simulation approach. We have compared a conventional powertrain with a dedicated hybrid engine powertrain, where we also, due to the electrification, can reduce the maximum power of the engine, because that is then provided by the electric system. And we can use this degree of freedom, so less power of the engine, in order to improve the efficiency in the sweet spot. So these figures are brake thermal efficiency here. And when we calculate the H2 consumption in the driving cycle, so WLTC, official European or EU driving cycle, we see that we can massively reduce the fuel consumption. For comparison with the fuel cell is still better. So if we compare it with the let's say best in class fuel cell powertrain, which is the powertrain from the Toyota Mirai, it has 0.85 kilograms per 100 kilometers, so still 20% better. But if you look at the cost of the system, the hydrogen engine powertrain is much cheaper. Quickly we have first results also achieved on the in driving cycles regarding pollutant emissions. In this case, as I have explained, we have kind of a lean burn concept with the elements in the after treatment system as have been described. We simulated a passenger car powertrain on the engine test bench and did run it in different driving cycles, like also RDE driving cycles like RTS 95, which is pretty well known, and also typical stop and go cycle derived from the traffic situation in London, the so-called traffic for London cycle. When we compare the results for the different criteria pollutant emission components and compare it with the gray bars, which are the limits of the upcoming Euro 7 legislation or Euro 7 plus legislation stages that are in the EU currently in discussion, we see basically, except for NOx, we have basically, let's say, close to zero emission situation. So CO below 0.5 milligram per kilometer, HC not visible. NH3 also will be limited with Euro 7, also very low values, and particulates also let's say much lower than the most stringent legislation. The only remaining component is NOx, and here we still have room for improvement. So we are pretty confident that we can achieve with hydrogen engine powertrains very, very low criteria pollutants. Yeah, that concludes my presentation. Maybe to sum up, we need a technology open approach. Bosch is working on it. And this technology open approach includes battery electric fuel cell and hydrogen engine, but also a drop in renewable fuels, as we have learned recently from the EU. Already with the latest Euro 6 technology, gasoline and diesel powertrains will lead to negligible contribution regarding air quality. Hydrogen engine will be even better because the initial conditions for the hydrogen engine are better. We see massive worldwide interest in this topic. We are working on the topic. We try to position ourselves as a system supplier here, and we are convinced that hydrogen engine powertrains will become an important part of future mobility. Thank you very much.
Okay, thank you very much, Eric. Very interesting presentation.